Welcome to today's deep dive. Get ready, because we're going deep into the world of magnetism. It looks like you've been hitting the books pretty hard for that physics exam coming up on October 4th. Some fascinating stuff in those lecture notes you shared.
Magnetism is one of those things that has been around, well, forever. But actually understanding it, that's a story that took centuries to unfold. And, it all starts with one simple question. What makes a magnet magnetic?
Okay. Let's break it down. I'm seeing a lot here about those naturally occurring magnets, the lodestones. It seems like people have known about those since, prehistory.
Yeah. You can imagine what it must have been like to find a rock that, magically attracts iron. That's a lodestone, just a chunk of iron oxide, really. But that mysterious force had people totally baffled for ages. And then there's the fact that the Earth itself is a giant magnet. That's how a compass works. The needle aligns with Earth's magnetic field to point north.
Wow, I never thought of it like that. Figuring that out way before they understood the science is pretty impressive. So how did we go from basic magnets and compasses to understanding the actual forces at work?
Well, that's where things get really interesting. Around 1800, there was a huge key shift in how we understand not only magnetism, but electricity, too. Alessandro Volta invented the battery, which meant suddenly people could generate those steady electric currents for the first time. Opened up a whole new world of possibilities, really. And then in 1819, Hans Christian Ørsted made this, groundbreaking discovery that totally changed the game. He noticed that a compass needle would actually move when it was near a wire with an electrical current running through it.
Wait, so that was the first time anyone realized that electricity and magnetism were actually connected? Like some kind of hidden dance between the two?
Exactly. This discovery kicked off a frenzy of research, and it wasn't long before they came up with the electromagnet. It's wild to think about how important that invention was. Imagine a world without electric motors or generators or even speakers. It all started with that connection between electricity and magnetism that Ørsted discovered.
Okay, hold on. I'm seeing something in my notes here about a right-hand rule. Does that tie into all of this?
It does. Ørsted also developed the right-hand rule as a simple way to figure out the direction of the magnetic field around a wire with current. It's almost like a magic trick. You just hold the wire in your right hand and make sure your thumb points in the direction of the current. The way your fingers naturally curl around the wire, that shows you the direction of the magnetic field lines.
That's actually a pretty cool way to visualize it. So if the current's flowing away from you, then the magnetic field circles around the wire clockwise. But how did this lead to actual inventions?
Well, now you have a way to create a magnetic field just by turning on an electrical current. So basically a magnet that you can switch on and off. And that is the basis for so many technologies. Like one of the earliest examples is in the 1830s when Samuel Morse used this idea to make the first commercial telegraph. That was a huge deal. It meant people could communicate over really long distances almost instantly.
So we went from magnets found in nature to magnets we can create and control using electricity. That's incredible. So we know electricity can make magnetism, but can it go the other way? Can magnetism create electricity?
That's the question that Michael Faraday was working on, and his discovery was huge EE. Turns out the opposite is also true. Changing magnetic fields actually produce electrical fields. It's like a yin and yang thing. They create each other.
Wait, this is where my brain starts to melt a little. How does that even work?
Think of it this way. If you move a magnet near a wire, the changing magnetic field basically pushes the electrons in the wire, and that creates an electric current. And this is exactly how we generate electricity. Those massive generators you see at power plants, basically just spinning magnets that create changing magnetic fields, which then induce electrical currents.
Mind blown.
Right.
It's like this crazy dance between electricity and magnetism, one creating the other back and forth. And Faraday discovered this way before the first power plant.
Yeah.
So what came after that? Did anyone else contribute to understanding this connection?
Of course. In 1876, Alexander Graham Bell used these same principles to invent the first practical telephone. And then just 10 years later, the first practical electric motors. They harnessed the interaction between magnetic fields to generate motion.
Wow. So we went from the telegraph to the telephone and from power plants to electric motors. All thanks to this crazy connection between electricity and magnetism. And this all happened before we knew what was going on at the atomic level, right?
Exactly. That's where the story takes another cool turn. It's like scientists were chefs who could make these incredible meals, but didn't know the chemical makeup of the ingredients. They could use electricity to make magnets and magnets to make electricity, but no one really understood why it worked. And then in 1928, Werner Heisenberg came along and changed everything with his theory that explained magnetism at the atomic level.
Okay, so what was Heisenberg's big breakthrough? What's actually happening inside these magnetic materials?
Well, his theory showed that magnetism is actually a quantum mechanical thing. It all comes down to the movement and spin of electrons. We need to go a little deeper into the world of atoms here.
All right, we're going full deep dive now. So, electrons, they have something to do with magnetism. Explain it to me like I'm 5 years old.
Okay, imagine electrons as tiny little spinning balls of charge. That spinning motion actually creates a tiny magnetic field around each electron. It's like each electron is its own mini magnet with a north and a south pole, just like any other magnet.
So it's like a bunch of tiny little compass needles swirling around inside an atom.
Exactly. Now, in most materials, these tiny magnetic fields are all pointing in random directions, and they basically cancel each other out. That's why most things aren't naturally magnetic. But in some materials, like iron, those tiny magnetic fields can all line up, and when they do, they create a much stronger, larger magnetic field. That's why iron is naturally magnetic.
Ah, so it's all about alignment, like having an entire army of those tiny compass needles all pointing in the same direction, creating a really powerful force. Wait, I'm seeing in my notes that protons spin too.
You're right. Turns out those protons, the positively charged particles in the nucleus of an atom, those are spinning too. And since they're spinning charges, they also create tiny magnetic fields.
Wow, so even the nucleus of an atom is a tiny magnet. It's like magnetism is built into the very fabric of matter. But how did scientists figure out how to measure the strength of these magnetic fields?
That's where André-Marie Ampère comes in. He was this brilliant physicist who developed formulas to calculate the strength of magnetic fields, specifically those generated by wires carrying electric current.
Formulas. Okay, now we're getting into the nitty-gritty.
One formula he came up with is B equals EI A2R. Don't worry, it's not as scary as it looks. This formula tells you the strength of the magnetic field, B, at a certain distance, R, from a long straight wire with current I flowing through it. And that symbol, Ia, that's a special constant called the permeability of free space.
Okay, so if I know how much current is flowing through a wire, I can use this formula to figure out how strong the magnetic field is at any point around that wire. Pretty cool.
Exactly. And we measure the strength of a magnetic field in a unit called a Tesla, represented by the letter T.
Teslas. So that's how we measure the power of a magnet. I bet different magnets have wildly different Tesla ratings, huh?
Absolutely. Just to give you some perspective, the Earth's magnetic field is only about 5 by 10 Earth Teslas. That's pretty weak. Your average fridge magnet is about 5 by 10 Earth Teslas, so about 100 times stronger than the Earth's field. But then you have those junkyard electromagnets that can get up to 1 Tesla. And scientists in research labs have even created these pulsed magnetic fields that reach an insane 92 Teslas.
92 Teslas. That's got to be crazy strong. I'm picturing metal objects flying across the room.
Oh yeah, incredibly powerful. Scientists use those ultra-strong magnetic fields for all sorts of cutting-edge research. But getting back to Ampere, he also figured out that if you take a wire and wrap it into a coil, something called a solenoid, you can create an even stronger and more uniform magnetic field inside that coil.
Right, I've got a diagram of a solenoid here in my notes. Basically a wire spring, right? How does that shape affect the magnetic field strength?
Well, the formula for the magnetic field inside a solenoid is BINSIDE equals RNL. N is the number of turns of wire in the coil, and L is the length of the coil. So the more turns of wire, or the shorter the coil, the stronger that magnetic field.
Now you're speaking my language.
Yeah.
So by changing the number of turns in the wire and how long the coil is, you can fine-tune the strength of the magnetic field, like a magnetic field dial. And this is all still based on that initial discovery connecting electricity and magnetism.
Exactly. It's really remarkable how that one discovery has led to so many incredible technologies, from simple electromagnets to those complex machines that power our world.
This is blowing my mind. Ancient compasses, powerful electromagnets, formulas that explain it all. But before we move on, I need to make sure I get this. What are magnetic fields exactly? What are they made of?
Great question. And it's one that puzzled scientists for a long time. You have a diagram in your notes that shows the magnetic field lines around a magnetic dipole. Picture it like a simple bar magnet. The field lines come out of the north pole of the magnet, curve around, and then enter the south pole.
Right, those classic looping lines you always see in the diagrams.
Yeah.
So they show the direction of the magnetic force, and the closer together those lines are, the stronger the field.
Exactly. It's like a map of the magnetic force. But here's where it gets interesting. A magnetic field is a region of space where you can detect a magnetic force. But unlike, say, a table which is made up of atoms, a magnetic field isn't made of anything tangible.
Wait, so it's like an invisible force field. How is that even possible?
Okay, think about it like this. A magnetic field is just a way to describe how magnetic forces work through space. It's a fundamental force, just like gravity. We can't see gravity, but we know it's there because we feel its effects. It's kind of the same with magnetic fields. We don't see them, but we can detect them because of how they affect magnets and moving charges.
Whoa, this is getting pretty deep. So it's a force field, but not like some Star Trek shield or
Mhm.
something. It's something more fundamental, something that's just built into the universe itself.
Exactly. It's one of the four fundamental forces of nature. It's responsible for everything from the northern lights to how your smartphone works. But here's what's really wild. It all comes down to those tiny spinning charges we talked about, those magnetic dipoles.
You mean those tiny magnets within atoms? They're the building blocks of all magnetic phenomena. So when we talk about a big magnet, like a Gauss magnet, we're talking about billions and billions of these tiny magnetic dipoles all working together.
You got it. And it's how those dipoles interact with each other and with external magnetic fields that creates all of the amazing things we see magnets do.
This is incredible. We've gone from ancient compasses to powerful electromagnets and formulas that explain how it all works. But I have a feeling this is just the beginning. What other cool stuff are we going to explore as we keep diving deeper into the world of magnetism?
Well, next we're going to talk about some of the weirder and even more mind-blowing aspects of magnetism. Get ready for some really crazy concepts. We're going to cover things like magnetic monopoles, superconductors, and even the possibility of magnetic levitation.
Okay, now you're talking. Let's do it.
Welcome back. So before we jump into all that really out there stuff, we were talking about this tiny little spinning charges, magnetic dipoles, right? The building blocks of all things magnetic.
Yeah, it's crazy to think that everything from like those little fridge magnets to those huge electromagnets they used to pick up cars at the junkyard, it all comes down to those tiny spinning charges working together. But how do they actually create those bigger magnetic fields? I mean, do they like have little meetings and decide which way to point?
Uh-huh. Well, maybe not meetings, but they definitely influence each other. Okay, picture this. You've got two bar magnets. What happens when you bring them close together?
Well, if I bring the north pole of one magnet close to the south pole of the other one, they attract, right? But if I try to bring two north poles together or two south poles, they push each other away, like they've got their own little personal space bubbles. Opposites attract, like poles repel. That's like magnetism 101. Yeah.
Exactly. And that same idea applies to those tiny magnetic dipoles inside atoms. When they're all jumbled up, their magnetic fields cancel each other out and the material doesn't act like a magnet. But when they all line up in the same direction, watch out, their magnetic fields reinforce each other, and that creates a much stronger overall magnetic field. And that's what happens in those ferromagnetic materials like iron, nickel, and cobalt.
Oh, so that's what makes them naturally magnetic. Their dipoles are all lined up and ready to go. But what about materials that aren't naturally magnetic? Is there any hope for them? Can we make them magnetic somehow?
Great question. It turns out even materials that aren't naturally magnetic can be magnetized, at least temporarily anyway. Remember how most materials have their magnetic dipoles all pointing in random directions? Well, if you apply a strong enough external magnetic field, you can actually force some of those dipoles to line up, like a drill sergeant getting them into formation. We call this induced magnetism.
Uh-huh. So we can bully those dipoles into lining up, but only for a little while. It's like they're rebellious teenagers. As soon as you stop watching, they go back to their messy rooms.
That's a great analogy. Think about rubbing a paperclip with a magnet. For a little while, the paperclip becomes magnetic and can pick up other paperclips. But eventually those dipoles go back to their random ways and the paperclip loses its magnetism.
Okay, I'm starting to get how this whole dipole thing works. Some materials are born magnetic, with their dipoles all neat and tidy, and others need a little encouragement to get organized. But going back to those lecture notes, there's this calculation for the period and current of an electron orbiting a proton in a hydrogen atom, and I have to admit, this one has me stumped. It says the period of the electron's orbit is 10 seconds, and the current is 1.6 by 10 coulombs, or about 1 by 10 amps. How can an electron just orbiting a proton create a current? I thought current was like a flow of charge through something, like a wire.
That's a really good observation, and it gets right to the core of how magnetism works at the atomic level. See, any moving charge creates a magnetic field. So even though that electron is bound to the proton in the hydrogen atom, its orbital motion is still movement of charge. And it creates a tiny little current loop, almost like a microscopic electrical circuit, and that loop generates its own little magnetic field.
Ah, okay, I see. It's like its own little miniature version of those wires we were talking about. Each electron is like a tiny power line.
Exactly. And even though the current and the magnetic field created by a single electron are super small, when you add up the contributions of billions and billions of electrons in a material, those tiny little fields can add up to something much bigger. It's like a massive synchronized swimming routine. Each swimmer creates a tiny ripple, but all together, they make some pretty impressive waves.
This is wild. Every atom is like a little city with electrons zipping around, creating those magnetic fields, and all contributing to the overall magnetic character of the material. But let's change gears a bit and talk about how we actually measure these magnetic fields. We've talked about Teslas, but is there anything else I should know?
That's a good point. There are some other terms and concepts that can help us understand magnetic fields. You might run into something called magnetic flux density, but don't let the fancy name scare you. It's basically just another way of talking about magnetic field strength, and it's also measured in Teslas.
Gotcha. So Tesla is the go-to unit when we're measuring magnetic field strength, whether it's flux density or just the overall strength of the field. But what about the direction of a magnetic field? We learned about the right-hand rule for wires, but is there a way to figure out the direction of the field around a magnet?
There is, and it's actually pretty similar to the right-hand rule for wires. Imagine holding a bar magnet in your right hand, with your fingers curling around it from the South Pole to the North Pole. Your thumb will then point in the direction of the magnetic field lines inside the magnet.
So those invisible field lines are running from south to north inside the magnet, and then they loop around from north to south on the outside. It's like they're going on a little adventure.
Haha, exactly. And just like with that right-hand rule for wires, the direction of the magnetic field lines tells you which way the magnetic force is pushing or pulling.
Okay, I think I'm finally getting a handle on this whole magnetic field thing. But why should we even care about this stuff? I mean, it's all very fascinating, but what's the practical application of magnetism in our everyday lives?
Ah, that's the big question. And the answer is it's everywhere. Magnetism is the invisible force that makes countless technologies possible. Electric motors, generators, speakers, hard drives, MRI machines, and so much more. It's like the silent hero of the modern world.
You're right. We totally take those everyday things for granted, but they just wouldn't exist without this fundamental force of nature. It's crazy to think what the world would be like without it.
Exactly. And it goes way beyond those everyday things. Magnetism is a vital tool in many scientific fields. Astronomers use magnetic fields to study distant stars and galaxies. Geophysicists use them to explore the mysteries hidden deep inside the Earth. And particle physicists, they use these incredibly strong magnetic fields to smash atoms together and study those fundamental building blocks of the universe.
Wow, so it's not just some cool science experiment. It's this force that powers our world, helps us understand the universe, and is even part of the very building blocks of matter.
It really is, and we've only just begun to understand this incredible force. There's still so much more to discover and explore.
Okay, I'm ready for those mind-blowing concepts you promised. Magnetic monopoles, superconductors, and even levitation. Hit me with it.
Get ready, because things are about to get a whole lot stranger. Buckle up, we're going into the realm of the truly bizarre.
Okay, I'm ready for those mind-blowing concepts. Bring on the magnetic monopoles, superconductors, and levitation. Let's hear it.
Haha, all right, get ready for things to get weird. We're going deep into the bizarre side of magnetism. So let's start with magnetic monopoles. Remember how we were talking about those magnetic dipoles, those tiny little magnets with a north and south pole? Well, a magnetic monopole would be a particle with only one magnetic pole. Just north or our south, but not both.
Wait, a magnet with just one pole?
Uh-huh.
But like every magnet I've ever seen has both. It's like having a coin with only heads or only tails. Is that even possible?
That is the million-dollar question. It sounds crazy, but the existence of magnetic monopoles is actually possible, theoretically. Scientists have been on the hunt for them for decades, but no luck so far. It's like they're playing hide and seek with us.
So they're like the holy grail of magnetism. Everyone's searching, but no one can find them. If we did find one, would that, rewrite the physics textbooks?
Absolutely. It would be huge. Finding a magnetic monopole would completely change how we understand magnetism. It would be like discovering a whole new continent on the map of physics.
Yeah.
And who knows what kind of amazing technologies we could unlock if we could, actually harness the power of these things.
Okay, I'm adding magnetic monopole hunting to my bucket list.
Yeah.
But now you've got me curious about those other wild ideas you mentioned, superconductors. What are those? What makes them so super?
Superconductors are materials that basically have zero electrical resistance below a certain temperature. It's like they're the ultimate smooth talkers when it comes to electricity. They let electricity flow through them with absolutely no energy loss. It's like a frictionless slide for electrons.
Zero resistance. Wow. So you're saying electricity could flow through them forever without losing any power. That's like a perpetual motion machine for electricity. But how does this connect to magnetism?
That's where it gets really wild. Superconductors and magnetic fields have this like strange relationship. Superconductors actually expel magnetic fields from their insides. It's called the Meissner effect, and it's one of the key things that make superconductors so unique.
So they're like immune to magnetism. Like they have some kind of force field that just pushes away any magnets that come near them.
Exactly. If you bring a magnet near a superconductor, the magnetic field lines will actually bend around the superconductor. Like it's an impenetrable barrier. Like they're saying, no magnetic fields allowed here.
Okay, this is some serious science fiction stuff. So if they can repel magnetic fields, does that mean you could use them to levitate a magnet? Like actual defying gravity levitation?
You got it. By carefully controlling magnetic fields and using superconductors, you can create a force that actually lifts and suspends an object. Just like magic. This is what's behind magnetic levitation, or maglev for short.
No way. You mean those maglev trains, the ones that like float above the tracks and go super fast, and they actually using superconductors to levitate?
Well, not quite. Superconductors could be used for maglev, but they need those super low temperatures to work, which makes them a little impractical for something as big as a train. Most maglev trains actually use really powerful electromagnets to create a repulsive force between the train and the track. That lets the train float and move with almost no friction.
So even without superconductors, we can still get magnetic levitation. That's straight out of a futuristic movie. From levitating trains to the potential for amazing new technologies using magnetic monopoles, it seems like the possibilities of magnetism are basically endless.
You're right. It's incredible to think that this invisible force that has fascinated people for centuries still has so many mysteries and so much potential. And to think it all goes back to those tiny spinning charges, those magnetic dipoles that create this force that shapes our world and captures our imagination.
This deep dive into magnetism has been a wild ride. My brain feels stretched, challenged, and definitely amazed.
Aha! That's what we're going for. It's always fun to explore the world of science and see how even those most basic ideas can have such huge implications.
To everyone listening, thanks for joining us on this deep dive into the world of magnetism. It's something we often take for granted, but as we've seen, it's super important to our understanding of the universe.
And remember, even though we covered a lot today, there's always more to discover. So keep exploring, keep those questions coming, and never stop being curious. Who knows what incredible discoveries are waiting for you?
That's a great way to wrap things up. Thanks for joining us, and until next time, keep those brains buzzing.